professor at LG Institute of Engineering and Technology. Today we are going to study few more topics of system of linear equations and matrices. So let's begin with the first topic, that is Cayley-Hamilton theorem. So the statement of the theorem is every square matrix satisfies its own characteristic equation. Okay, so firstly we'll start with the characteristic equation. Okay, so now we know for a 2 cross 2 matrix, what is the characteristic equation? Lambda square minus s1 lambda plus s2 equals to 0, where s1 is what? It is the sum of principal diagonal elements. Okay, and S2 is what? S2 is determinant of matrix A. Okay, and for 3 cross 3 matrix, the characteristic equation is lambda cube minus s1 lambda square plus s2 lambda minus s3 equals to 0. Okay, where s1 is sum of principal diagonal elements, right? And S2 is what? It is sum of minors of principal diagonal elements, right? And S3 is what? Determinant of this matrix A. Okay, so whenever we will replace our lambda by A matrix in this characteristic equation, okay, so you will get the equation as A cube minus S1A square plus S2A minus S3I. And if you will solve this, so you should get answer 0. Okay, so this statement says that this every square matrix, okay, it satisfies its own characteristic equation, right? So let's begin with the example. Verify Cayley-Hamilton theorem for the following matrix, and we have to find A inverse and A raised to 4. So let's begin with the solution. Here A matrix is given, that is 2 minus 1 1 minus 1 2 minus 1 1 minus 1 and 2. So the first step is to find characteristic equation, right, which is given by determinant A minus lambda I equals to 0. Okay, so firstly we will find this A minus lambda I. A matrix is given, we have to just subtract this by lambda I. I is identity matrix, which is given by 1 0 0 0 1 0 and 0 0 1. Okay, now just multiply lambda over here, so you will get lambda at these 3 places and subtract this 2. So what you will get? You will get here 2 minus lambda, 2 minus lambda and 2 minus lambda. Other terms will remain as it is because we have 0 at this place. Okay. Now we will write the characteristic equation using this formula. Okay, that is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. So firstly we will find s1, that is sum of principal diagonal elements of A. Okay, and it is also known as trace of A. So firstly we will write this matrix A, which is given by 2 minus 1 1 minus 1 2 minus 1 1 minus 1 and 2. Okay, so the principal diagonal are 2 2 and 2, right? So we have to add them. So on adding you will get answer 6. Okay, next we will find S2. So S2 is what? It is the sum of minors of principal diagonal elements. So we have to find the minors of these two, this 2 and this 2, and we have to add them. Okay, so firstly we'll find the minor of this 2. So for that you have to hide this row and this column. So you will get 2 minus 1 minus 1 2 plus. Now we will find the minor of this 2. Okay, so just hide this row and this column. So you will get 2 1 1 2 here, right? And plus, to find the minor of this 2, we have to hide this row and this column. So you will get 2 minus 1 minus 1 2 here, right? Now we will solve this 3 determinant. So here you will get 4 minus 1, okay, plus again here 4 minus 1 and also here 4 minus 1. Simplify this, so you will get the answer of S2 as 9. Right? Now we will find S3. So S3 is what? Determinant of A. A matrix is given, we will find its determinant. So firstly we will keep this 2 as it is and multiply this 2. So you will get 4 minus 1. Okay, here we have minus 1, so it will become plus 1 into here minus 2 plus 1. Okay, and plus 1 into here 1 minus 2. Right? Now simplify this, so you will get answer of S3 as 4. Okay, now we will substitute the value of S1, S2 and S3 in characteristic equation, okay, which is given by lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. Okay, so just substitute the value of S1, S2 and S3. So you will get lambda cube minus 6 lambda square plus 9 lambda minus 4 equal to 0. Okay, now what we'll do, we'll replace this lambda by a. So you will get here a cube minus 6a square plus 9a minus 4i. Okay, now what we have to do to verify this Cayley-Hamilton theorem, we have to solve this and the answer of this term should be 0. Then we can say that this Cayley-Hamilton theorem is verified. Okay, so now let's find a square first. Okay, so for that we have to multiply this a 2 times. So this A matrix is written here and now we will multiply it. Okay, so firstly consider this row and this column. Okay, and multiply its first term and then second term and third term and add them. So 2 into 2, here you will have 4. Then minus 1 into minus 1, so you will get plus 1, and 1 into 1, so again plus 1, right? Simplification, you will get answer 6. Next, consider this row and now we have to consider this column. Okay, so multiply the term. So 2 into minus 1, it will give you minus 2. Then minus 1 into 2. Okay, so it will give you minus 2 and plus 1 into minus 1. So it will give you minus 1. Simplify this, so you will get minus 5. Okay, so similarly you have to consider this row and this column and you have to solve. So you will get this 5 here. Then we have to consider this row and again we have to consider this 3 column one by one. So you will get this 3 value, right? Similarly you have to solve for this also. So you will get the answer of a square. Now we will find a cube. So for that we have to multiply a square with a. Okay, so answer of a square is this. Just substitute it, this a. Again we have to multiply it. On multiplication you will get 22 minus 21, 21 minus 21, 22 minus 21, 21 minus 21 and 22. This is the answer of a cube, right? Now what we'll do, we'll substitute this a cube a square in the characteristic equation, that is a cube minus 6a square plus 9a minus 4i, right? So just substitute the answer of here a cube. Now we will multiply 6 to this a square, so you will get this matrix, plus now multiply 9 with this matrix A, so you will get this matrix, and minus 4i means you have to multiply 4 to this identity matrix, so you will get this term. Okay, now we will simplify this. So for that what we'll do, first consider this first terms from each and every matrix. Okay, so 22 minus 36, then plus 18 minus 4. Simplify this, so you will get 0. Similarly, we have to consider each and every second term of the matrix, right? And we have to simplify like this, so you will get this 0 matrix. Okay, so what we can say that from this, that this matrix A satisfies its own characteristic equation, right? And therefore we can say that Cayley-Hamilton theorem is verified, right? Now we will find A inverse. Okay, so for that what we will do, we will multiply that equation 1 by A inverse. So you will get A inverse, that equation 1, that is a cube minus 6a square plus 9a minus 4i equal to 0. Now multiply A inverse inside. So what you will get here, a square then minus 6a plus 9i minus 4a inverse equal to 0. Okay, now make this 4a inverse as a subject. So you will get 4a inverse is equal to a square minus 6a plus 9i, right? Now we will substitute the value of this a square a. Okay, so you will get this. Now here we have to multiply this a matrix by 6, so you will get this matrix plus 9i, means we have to multiply it by 9 to identity matrix, so you will get this matrix. Okay, now again we have to simplify this. So here first term, that is 6 minus 12 plus 9, so you will get here 3, then minus 5, then here plus 6 and plus 0, so you will get here plus 1. Okay, so similarly we have to solve for each and every term, so you will get the answer of 4a inverse as this, but we have to find a inverse. Okay, so a inverse is equal to 1 upon 4 and this matrix, right? Now we have to find a raised to 4. So for that what we'll do, we'll multiply that equation 1 by a. Okay, so just multiply it by a. So what you will get, a into this a cube minus 6a square plus 9a minus 4i equal to 0. Multiply by a, so you will get a raised to 4 minus 6a cube plus 9a square minus 4a equal to 0. Make this a raised to 4 as a subject, so you will get a raised to 4 is equal to 6a cube minus 9a square plus 4a. Now we will substitute the answer of this a cube, a square and a. Also we will multiply 9 to this a square and 4 to this a. So you will get a raised to 4 as this. Okay, we have to simplify this 3 matrix. So you will get the answer of a raised to 4. Correct? So in today's session what we have studied? Cayley-Hamilton theorem. So the statement of the theorem is that every square matrix should satisfy its own characteristic equation. Okay, so firstly, suppose if we have 3 cross 3 matrix, right? So we have this characteristic equation as lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. So what we have to do, firstly we have to find this characteristic equation by solving this s1, s2 and s3. Okay, and then in place of lambda we have to substitute a, so you will get the equation in the form of a. Okay, that is a cube a square a. So we have to solve that, and on simplification you should get answer as a 0. Then only we can say that this Cayley-Hamilton theorem is verified. Okay, so I hope you have understood throughout the session. Thank you for watching.